Welcome to the Sleepy Scholar. It's lovely to have you here tonight. Wherever you are, whatever hour it happens to be in your corner of the world, I'm glad you found your way to this quiet little place. Go on and settle in. Pull the blanket up a bit higher if you like. Let your shoulders come down from wherever they've been holding themselves all day. There's nothing you need to do now. Nothing you need to solve, or finish, or remember. You can put all of that down for a while. I want you to imagine something for me before we begin. Somewhere out in the dark of space, unimaginably far away, a small, distant galaxy flickers, and in that flicker, in less time than it takes your heart to beat once, a flash of radio waves leaps out into the void. Just a flash, 1,000th of a second, maybe a few thousandths, shorter than a blink, shorter than the little pause between one breath and the next, and then it's gone, and the galaxy goes back to being quiet, as if nothing happened at all. But that flash doesn't stop. It travels, it crosses the emptiness between the stars, and then the far greater emptiness between the galaxies, on and on. For millions of years, sometimes billions, sailing through the thin cold dark. And one ordinary night, long after the thing that made it has changed beyond recognition, that little flash washes over the earth. It passes through the walls, through the roof, through you, gentle as moonlight, and lands in the dish of a radio telescope somewhere on the ground. A ripple that began before there were people to see it, arriving at last. We call these flashes fast radio bursts. And tonight, slowly and softly, one idea at a time, I want to tell you the strange and rather beautiful story of how these tiny flashes, each one over almost before it began, solved a mystery that had haunted astronomers for decades. A mystery about something missing, something enormous, something that should have been easy to find, and wasn't. Because here is the scandal at the heart of tonight's story. For years, and I mean a good long stretch of years, astronomers could only find about half of the ordinary matter in the universe. Half, not a rounding error. Not a little sliver at the edges. Half of all the normal, everyday stuff that everything is made of was simply missing from every map they had ever drawn. They knew, with real confidence, how much there ought to be. They could add up how much they could actually see, and the two numbers didn't match. The universe seemed to be carrying only about half the matter it was supposed to have, and nobody could say where the rest had gone. Isn't that a lovely thing to fall asleep on, a missing half of everything? And by the end of our slow wander tonight, we'll have found it. So there's no worry hanging over this story. It has a happy ending. We just get to take the long, gentle road there. Now, before we go any further into the dark, let me say one quiet thing. If you're enjoying these slow journeys, and you'd like more nights like this one, a gentle like and a subscribe really do help this sleepy little channel keep going. I'm a small creator, and honestly, that little tap from you matters more than you'd think. It's the whole reason I get to keep making these. And to those of you already subscribed, sitting here again tonight, thank you. Truly, it means the world. While you're settling in, I'd love to know, where in the world are you listening from tonight, and what time is it in your corner of the dark? Leave it in the comments if you feel like it. I always love to imagine all the different windows, all the different rooms, all the different hours where these words find people. But there's no pressure at all. Mostly I just want you to rest. And I'll make my usual promise. I'll try not to make this so interesting it keeps you awake. But if it does, well, at least you'll have learned something lovely. A fair trade, I think. And if you drift off before the end, that's perfectly all right. That's what this is for. The ideas will still be here. The universe is very patient. It's waited billions of years already. It can wait for you to wake up. So, let's begin, shall we? Softly. Now, the very first thing I have to clear away, because it trips almost everyone, and I don't want it snagging at the back of your mind while you're trying to drift off, is a little tangle of names. When you hear that half of the universe's matter was missing, there's a good chance your mind reaches for a phrase you've heard before. Dark matter. That mysterious, invisible stuff nobody can find. And you might think, this must be the dark matter story. This must be that. But it isn't. And this is the single most important thing I can tell you tonight, so let me say it slowly and plainly. The way you'd explain something to a friend sitting on the edge of your bed. The matter that went missing in our story is not dark matter. It's ordinary matter. The plain, familiar stuff. The stuff you are made of, the stuff your pillow is made of, and the walls, and the water in the glass by your bed, and the air moving softly in and out of you right now. Atoms, protons, and neutrons, and the little electrons that go with them. Scientists have a name for it. They call it baryonic matter. That word, baryon, just refers to the particles at the heart of every atom. The protons and neutrons packed into the tiny nucleus. So when I say baryonic matter, I only mean the same thing your grandmother would have called stuff. Things made of atoms. Ordinary matter. Dark matter is something else entirely. Dark matter is a genuine, still open mystery, some kind of invisible mass that we can feel by its gravity, tugging on galaxies, but which doesn't seem to be made of atoms at all. Nobody has ever held a piece of it. Nobody knows quite what it is. And I want to be honest with you, that mystery is not the one we're solving tonight. That one is still wide open. We'll nod to it once, as a neighbour, and then let it be. Because our mystery is a different flavour altogether. Our missing matter was never a question of whether it existed. We knew it existed. We knew it was there, somewhere, made of perfectly ordinary atoms. We just couldn't find where it was hiding. Think of the difference like this. Dark matter is like a strange sound in the house that you've never been able to explain. You don't know what's making it. You can't even say what it is. But our missing baryons, our missing ordinary matter, that was more like knowing for absolute certain that you own 20 books, counting the shelf, and finding only 10. You're not confused about whether the books exist. You bought them. You remember them. They're yours. They're just not where you can see them. 10 books, somewhere in the house, unaccounted for. That nagging, particular kind of puzzle, that's the one we have tonight. And it even has a proper name, this puzzle, a name astronomers gave it because it bothered them for so long. They called it the missing baryon problem, the missing ordinary matter problem. Isn't that a wonderfully honest name for it? Not the mysterious matter problem, not the exotic problem, the missing problem. We know how many there should be. We can't find them all. Where did they go? Now, you might already be wondering the obvious thing. If you can't see this matter, if it's invisible and lost, how could anyone be so sure it was missing in the first place? How can you know you're short 10 books if you never counted them onto the shelf to begin with? That's exactly the right question to ask, and the answer is one of the loveliest pieces of science I know. Because we didn't guess at the total. We have two completely separate ways of measuring how much ordinary matter the universe ought to contain. Two witnesses, standing in two different rooms, who never spoke to each other, and yet they tell almost exactly the same story. When two witnesses agree that closely, you start to trust them. Let me tell you about the first witness. And to meet it, we have to go back. Way back. further back than almost anything you can picture, to the first few minutes after the universe began. Now, no need to grasp every detail here. Just let the picture form gently. Imagine the whole universe, in its very first moments, as an unimaginably hot, dense fog. Not stars, not planets, not even proper atoms yet, just a searing soup of the tiniest particles, packed so tight and so hot that nothing could hold together. And in those first few minutes, and it really was only minutes, the whole thing happened faster than it takes a kettle to boil. That soup began to cool. Just enough. And as it cooled, the very first atomic nuclei started to form. Protons finding neutrons, little clumps sticking together for the first time. Mostly, what formed was hydrogen, the simplest thing there is, just a single proton. Alone. And a good amount of helium, the next simplest, 2 protons and a couple of neutrons bound up together. And then, just the faintest trace of a few other light things, a whisper of a heavier kind of hydrogen called deuterium, a breath of lithium. And then the window closed. The universe cooled past the point where any more could form, and that was that. The recipe was set in the first handful of minutes, and it has barely changed since. Scientists call this moment Bang Nucleosynthesis. A big name, I know, but pull it apart and it's gentle enough. Nucleo, the nucleus, the heart of the atom. Synthesis, making, building, the building of the first atomic hearts, in the Big Bang. That's all it means. The universe's first act of cooking, done in minutes, never repeated. And here's the beautiful part, the part that makes it a witness. That first recipe was exquisitely sensitive to exactly how much ordinary matter there was. If the early universe had been packed with more atoms, the mixture would have come out a little different. A touch more helium, a touch less deuterium. Pack in fewer atoms, and the balance tips the other way. The precise ratio of these light elements, the exact amount of hydrogen to helium, to that faint trace of deuterium, is like a fingerprint of how much ordinary matter existed in those first few minutes. It's baked into the mixture forever. So astronomers go out and they measure those ratios. They look at ancient, pristine clouds of gas that have barely been touched since the beginning, and they carefully weigh out how much deuterium there is compared to ordinary hydrogen. And from that delicate ratio, they can read backward all the way to those first minutes and calculate exactly how much ordinary matter the universe was born with. The recipe tells them, the shopping list. That's the first witness, the ashes of the very first fire, still holding the memory of how much fuel there was. And now, the second witness. This one comes from a different time altogether, not the first few minutes, but a good while later. Around 380,000 years after the beginning. Which sounds like an eternity, and by our small human reckoning it is. But against the age of the whole universe, it's still the earliest infancy, the first faint light of a very long day. For all those first hundreds of thousands of years, the universe stayed too hot and too crowded for light to travel freely. It was like a thick fog. Light couldn't get more than a little way before bumping into a particle and scattering off in some new direction. If you'd been there and somehow survived, you'd have seen a blinding, featureless glow in every direction, a fog you could never see through. The universe was opaque, shrouded, and then, at around 380,000 years, it cooled just enough for something wonderful to happen. The loose protons and electrons, which had been careening around freely, finally slowed enough to join hands. They settled into the first complete, stable atoms, proper hydrogen, proton and electron together at last, and all at once the fog cleared. With the loose particles tidied away into atoms, light could suddenly stream across the universe unobstructed, free to travel forever. The universe became transparent. The lamps, in a sense, came on. And that very first light, the flash from the moment the fog lifted, is still travelling. It's still washing over us, right now, faint and cold, stretched out by the long journey and the expansion of everything into a whisper of microwaves. We call it the cosmic microwave background, the oldest light there is, a baby photograph of the whole universe, taken when it was only 380,000 years old. And it is, quite literally, all around you tonight, in this room, passing through you as you rest. The afterglow of creation, soft as breath. Now here's why the cosmic microwave background is our second witness. When astronomers look at that ancient light very, very carefully, they find it isn't perfectly smooth. There are the faintest ripples in it, regions that are a tiny fraction of a degree warmer, others a tiny fraction cooler. And those ripples are not random. They're the frozen echo of sound waves that were rolling through that early fog, waves of pressure sloshing back and forth in the hot young universe. The pattern of those ripples, how big they are, how they're spaced, how loud one is compared to the next, depends on exactly what the universe was made of. How much ordinary matter, how much dark matter, how much of everything. There's a whole spacecraft that measured this for us with exquisite care, the Planck satellite, a beautiful instrument that spent years drinking in that ancient light and mapping its faintest ripples across the whole sky. And from that map, from the precise pattern of the warm and cool patches in the oldest light in existence, scientists could read off the recipe of the entire cosmos. And here's what they found. It's one of the strangest, humblest facts I know, and I'd like you to just let it settle over you softly. Everything you have ever seen, every star, every planet, every galaxy, every living thing, every atom of your own body, all the ordinary matter there is, all of it together makes up only about 5% of the universe. Roughly 4.9% if you want the careful number. 5%. That's the whole visible show. The stars and the planets and the people, the entire glittering everything. It's a thin skin of foam on the top of a very deep and very dark ocean. The rest? About 27% of the universe is that dark matter we spoke of, the invisible stuff, not made of atoms, that we only feel by its gravity. And the remaining 68%, the great overwhelming majority, is something even stranger called dark energy. A kind of pressure woven into empty space itself that seems to be pushing the whole universe to expand faster and faster. But those two, the dark matter and the dark energy, those are neighbours in a different story. We only need them tonight so you can see how small our own 5% really is. 5% ordinary matter, 27% dark matter, 68% dark energy. We live in the 5, the little bright rind on an enormous dark fruit. Now here is where the two witnesses do their quiet, remarkable thing. Remember, they came from completely different moments and completely different methods. The first witness read the recipe from the ashes of the first few minutes, from the ratio of hydrogen to helium to deuterium, the fingerprint of Big Bang Nucleosynthesis. The second witness read it from the ripples in the oldest light, 380,000 years later, the cosmic microwave background, mapped by Planck. Two witnesses, two eras, two utterly unrelated ways of counting. And they agree. On the amount of ordinary matter, they agree to within a few percent of each other. The recipe from the first minutes and the pattern in the ancient light tell the very same story about how much ordinary matter the universe holds. When two measurements that have nothing to do with one another land in the same place like that, scientists stop worrying about whether they're right. That agreement is about as close to bedrock as cosmology gets, so we can say it with real confidence and hold it as solid ground under the rest of the night. We know how many books belong on the shelf. We know how much ordinary matter the universe contains. The total is not in doubt. And that, of course, is exactly what makes the missing half so maddening. Because now we come to the counting. Now astronomers roll up their sleeves and go out to actually find all that ordinary matter, to point at it and tally it up. And this is a slow, patient business, done across many years and many telescopes. They count the stars, all the countless suns burning in all the countless galaxies. They count the galaxies themselves, and the great glowing clouds of gas inside them, the cold, dim gas and the warm gas both. They count the enormous pools of hot gas that sit inside clusters of galaxies, gas so hot it glows in X-rays. They add up everything they can point to and say, "There, that's ordinary matter, I can see it, tally it up." Every star, every cloud, every visible thing, carefully summed. And when they finished the count, when they added up every scrap of ordinary matter they could actually find in the nearby universe, the universe close to us in space and in time, they came up with only about half of what the two witnesses said should be there. Only half. Some careful studies put the shortfall at around a third, some closer to a half, but the shape of it never changed. A vast fraction of the ordinary matter that we know exists, that two independent measurements insist exists, simply could not be found on any map. It wasn't in the stars, it wasn't in the galaxies, it wasn't in the bright hot pools inside the clusters. Everything we could point to, added together, came up desperately short. There were real people, careful astronomers, who spent years on this counting, laying out the census of ordinary matter piece by piece, and finding, again and again, the same troubling gap at the bottom of the ledger. Add it all up, and half the ordinary universe was simply gone. Present in the books, absent on the shelf. Now, sit with how strange that is for a moment, because it's stranger than it first sounds, and the strangeness is the whole reason this is worth a story. We're not talking about some exotic, hard-to-imagine substance. This is ordinary matter. Atoms, the same kind of stuff as your hand resting on the blanket. And there was apparently twice as much of it out there as anyone could locate. Enough to build another entire visible universe's worth of stars and galaxies, just unaccounted for. Missing, hidden somewhere in plain sight, in a cosmos we thought we'd mapped rather well. Where do you even begin to look for a missing half of everything? How do you lose something that big? And here's a gentle twist that only deepens the puzzle. A detail I find quite lovely. The matter wasn't missing everywhere. It was only missing here, only nearby, only now. Let me explain what I mean, because this is a real clue, and it's the sort of clue that only makes sense once you understand a peculiar gift that astronomy gives us. When you look out into space, you are also looking back into time. The light from a distant galaxy left it long ago. So you see that galaxy not as it is now, but as it was when the light departed, thousands, millions, billions of years in the past. The farther away you look, the further back in time you see. To look out across space is to look down through the ages, like reading the rings of a very old tree. The far distance is the deep past. Astronomers have a word for how far back you're looking. They call it redshift, and you don't need the machinery of it tonight. Just hold on to the simple idea that a higher redshift means farther away and farther back in time toward the younger universe. Low redshift is nearby and recent. High redshift is far away and long ago. That's all you need. Redshift is just a dial that turns toward the past. So astronomers did something clever. They looked far away, which is to say far back in time, at the universe as a much younger thing, and they tried to count the ordinary matter there. And they had a rather beautiful way of doing it. Out in deep space there are quasars, the blazing hearts of distant galaxies, some of the brightest beacons in all the cosmos. And the light from a quasar, on its long way to us, has to pass through all the thin gas that lies between here and there. Whenever that light crosses a cloud of hydrogen gas, the hydrogen drinks a little sip of the light at one very particular colour, leaving a thin, dark gap in the beam. And there are so many clouds along the way, at so many different distances, that the quasar's light arrives etched with a whole dense thicket of these little dark absorption lines, one after another after another. Astronomers, in their poetic way, call this thicket the Lyman Alpha Forest, a forest of shadow lines, each one the fingerprint of a cloud of ordinary hydrogen the light passed through on its long journey. And by reading that forest, by counting all those little shadows in the light of distant quasars, astronomers could tally up the ordinary matter in the far, early universe. And when they did, out there in the deep past, at high redshift, they found it, nearly all of it. The books balanced. In the young universe, the ordinary matter was all present and accounted for, right where the two witnesses said it should be, written plainly in the shadows across the quasar's light. So do you see the shape of the puzzle now? The matter wasn't missing in the early universe. It was all there long ago when the cosmos was young. It only went missing later in the local universe, the nearby universe, the present-day cosmos, close to home. Somewhere between the young universe and the one we live in now, about half of the ordinary matter slipped out of sight. It didn't vanish from existence, the total never changed, the books were never wrong. It just stopped being visible. It went quiet, it hid. And that, really, is the deepest and most tantalizing clue of all. The missing matter isn't missing from the beginning of the story. It's only missing from the end, from our chapter, the here and now. Which means it didn't disappear. It went somewhere. It moved into some form, some place, some hiding spot that our telescopes simply couldn't see. It was out there the whole time, all those billions of tons of ordinary atoms drifting somewhere just past the edge of what we could detect. Present, but unseen. Right in front of us, and utterly invisible. Half the ordinary universe, hiding in the dark, waiting to be found. And that is the mystery, laid out gently and whole. We know how much ordinary matter there should be. Two witnesses, the ashes of the first minutes and the light of the first dawn, agree on it beyond real doubt. We know it was all there in the young universe, written in the Lyman Alpha Forest across the faces of distant quasars. And yet, here, now in the nearby cosmos, half of it cannot be found in anything we can see. It didn't cease to exist. It went into hiding. Somewhere out there, the missing half is waiting, in some form so faint and so strange that every great telescope ever built looked straight through it and saw nothing at all. So where did it go? What could possibly hide that much ordinary matter so completely for so long from instruments built to see across the entire universe? Where do you tuck away half of everything? That's the question we'll follow next, into the vast, thin, cold spaces between the galaxies, into a place with a strange and wonderful name, where gas can be 1,000,000 degrees and still, somehow, be all but invisible. But there's no rush at all. Let that question just hang there in the dark for now, soft and unhurried, like a lamp left on in another room. We have all the time in the world to answer it. The missing matter has waited billions of years already. It can wait a little longer while we breathe and settle and drift on slowly toward it, one quiet mystery at a time. So, let's follow it. The question we left hanging, where do you hide half of everything, turns out to have an answer. And the answer is, in a way, everywhere that a galaxy is not. Let that land for a second before we go on. Between the galaxies, in the vast spaces that most of us, quite reasonably, think of as empty, there is a structure. The largest structure in existence, actually, larger than any single galaxy, larger than any cluster of galaxies, larger than anything else that has a name. Astronomers call it the cosmic web. And it earns that name. When you see the great simulations that model it, that trace the distribution of matter across hundreds of millions of light years, what you see does look remarkably like a web. Filaments of material, vast curving threads stretching across the universe and meeting at nodes, bright, dense concentrations where galaxy clusters sit, luminous and massive, like cities at the intersection of great roads. And between those filaments, the voids, regions of almost nothing, stretching for tens or even hundreds of millions of light years, where almost no galaxy lives and almost no light falls. We can trace the web with galaxies. Look at a map of where galaxies sit in the nearby universe. The great surveys like the Sloan Digital Sky Survey have charted millions of them, and the pattern leaps out. Galaxies are not scattered randomly. They are arranged. They trace the filaments. They cluster at the nodes. They avoid the voids. The large-scale structure of the universe is not chaos. It is, in its own patient way, organized, but the models, the simulations that follow the physics of how the universe evolved from that smooth young state all the way to this, always predicted something more than galaxies along the filaments. They predicted gas, an enormous quantity of diffuse gas threaded through those same filaments, filling the space between the galaxies, stretching and thinning across volumes so huge that even though the total mass it represents is staggering, the local density at any given point is nearly imperceptible. Gas that had never cooled enough to condense into stars. Gas that had been heated by the gravitational processes of cosmic history, by the shockwaves of colliding filaments, by the outflows of early galaxies pouring energy into their surroundings, by 1 billion years of slow compression and stirring, heated until it reached temperatures that are, by any human standard, extraordinary. 100,000 degrees. Sometimes 1,000,000 degrees, in some regions perhaps 10 million degrees. This is not a comfortable kind of heat. Here on Earth, a gas at 1,000,000 degrees would be a plasma so energetic it would vaporize whatever container you tried to put it in, and the container after that, and probably the building. At 1,000,000 degrees, atoms are fully stripped of their electrons. Matter becomes a soup of bare nuclei and free electrons crackling with energy. We encounter brief, small versions of it in the cores of nuclear reactors and in the coronas of stars. But out in the space between galaxies, this 1,000,000-degree gas carries almost no mass in any given cubic meter. Almost none at all. The density is so extraordinarily low. So many orders of magnitude below what we would call thin, even by the standards of the laboratory vacuums we are most proud of, that the number of particles in a typical cubic meter of this gas is smaller than you would find in the best vacuum chamber ever built on Earth. And yet, because the universe is so vast, and because these filaments stretch across such incomprehensible distances, the total accumulated mass of this gas adds up to something very large indeed. This is the Warm-Hot Intergalactic Medium, the WHIM, and the name, if you let yourself hear it, has a kind of rightness to it. It sounds like something slight, something that barely registers. The whim of the universe, an afterthought, a passing fancy, a gas so insubstantial that it seems like it should not matter. And yet the simulations by Renyu Sen and Jeremiah Oestreicher, published in 1999, and the work of Romil Dav and his collaborators, published in 2001, kept arriving at the same conclusion from their computer models of how the universe grew and evolved. A very large fraction of all the ordinary matter that had ever been forged in the first minutes after the Big Bang. Perhaps most of the missing half, perhaps more, should be sitting out there in exactly this form. In those filaments, in that million-degree gas, spread through the cosmic web in a substance so thin and so hot and so geometrically vast that it sat almost on purpose at the edge of what any telescope had ever been able to see. Beautiful, in its way, the universe tucking its accounting error into the most inconvenient drawer imaginable. But also frustrating, because knowing something is probably there and being able to detect it are entirely different things. And the whim was not just difficult to detect, it was difficult to detect in a very specific, almost exquisitely unfortunate way. The trap deserves a proper explanation, because without it you cannot fully appreciate why the eventual solution felt, to the astronomers involved, like something close to a miracle. Think about how we find gas in the universe. There are two great workhorses, two broad families of detection. On one side, hot dense gas, the kind you find in the cores of galaxy clusters. Gas at temperatures of tens of millions of degrees, packed into regions dense enough to be opaque at X-ray wavelengths, glows brilliantly in X-rays. It is hot enough, and it has enough particles close enough together to radiate powerfully, and X-ray satellites in orbit above the Earth's atmosphere can photograph it beautifully. The halos of hot plasma that surround rich galaxy clusters are some of the most spectacular objects in the X-ray sky. We know them well. We can weigh them. They are not the problem. On the other side, cold neutral hydrogen, gas at a few hundred or a few thousand degrees, gas where the proton and the electron have found each other and settled into the comfortable partnership of a whole atom, has its own telltale signature. It emits and absorbs radio waves at a very specific wavelength, 21 centimeters, the famous hyperfine transition of hydrogen caused by the slight energy difference between two orientations of the electron's spin relative to the protons. Radio telescopes map this signal across the sky and trace neutral hydrogen through the Milky Way, through nearby galaxies, through the local universe. We know it well too. It is not the problem. The WHIM sits between these two worlds. At 100,000 to 10 million degrees, the hydrogen is almost entirely ionized. The electrons have been knocked free, and there are no intact neutral hydrogen atoms left to emit or absorb at 21 centimeters. The radio surveys are blind to it. But at that temperature, and at that density, the gas is not producing nearly enough X-rays to be detected by even the best X-ray telescopes we have launched. To glow brightly in X-rays, you need to be either very hot, cluster gas at 100 million degrees, or very dense, or both. The WHIM is neither. It is warm by the standards of intergalactic space, but not incandescent. And it is thin beyond imagination. So, too hot for the radio surveys, too thin and too cool for the X-ray images. The WHIM had found, entirely by accident, an almost perfect hiding spot. Not mysterious in principle, not dark, not exotic, not violating any physics, just ordinary atoms of hydrogen and helium and traces of heavier elements, sitting at temperatures and densities that happen to fall precisely in the gap between the two great methods astronomers had for finding gas. You might think of it like this. Imagine you have two kinds of detectors in your house. One picks up sounds below a certain frequency, rumbles and bass. The other picks up sounds above a certain frequency, trebles and high notes. And someone is speaking to you in exactly the middle range, at frequencies your detectors can't register. They are right there, talking to you. And you have no way of hearing them. Not because they are speaking too softly, just because every detector you own is tuned to something other than their voice. That was the WHIM. Speaking right at the frequency nobody was listening for. And of course, astronomers knew this. They have always been resourceful people, and they were not going to let a frequency gap stop them without a fight. There was a third approach, not imaging the WHIM's own radiation, which was too faint, but searching for the shadows it cast. When hot gas sits between us and a very bright, very distant background source. It absorbs specific wavelengths of X-rays, the fingerprint of highly ionized atoms. An atom of oxygen that has lost 6 of its 8 electrons, what spectroscopists write as O7, often read as O7, absorbs X-rays at a characteristic wavelength. If you pointed a sensitive X-ray telescope at a blazingly bright background source and found a dip in the spectrum at exactly that wavelength, you had found hot ionized gas along the line of sight. You had, perhaps, found the WHIM. This technique, absorption spectroscopy in X-rays, is extraordinarily demanding. You need a background source bright enough to provide enough X-ray photons to build a reliable spectrum. You need the gas to be dense enough in that particular direction to absorb a measurable fraction, and you need an X-ray spectrometer sensitive enough to pick out the signal from the noise. These are not easy requirements to meet simultaneously. But in 2018, a team led by Fabrizio Nicastro did something that generated genuine excitement across the field. They used the European Space Agency's XME Newton, one of the largest and most sensitive X-ray observatories ever placed in orbit. Named for Isaac Newton and pointing patiently at the X-ray sky from its elliptical orbit far above the Earth to look toward a distant object called 1ES 1553 plus 113. The name is not evocative, admittedly, but the object is remarkable. It is a blazar, a type of active galactic nucleus, a galaxy with a supermassive black hole at its center that happens to be oriented so that a powerful jet of energetic particles is pointed almost directly at Earth. A blazar is, in effect, the brightest kind of cosmic flashlight nature has ever constructed, and this particular one, at a very large distance from us, blazes brightly enough in X-rays to serve as a background lamp for exactly the kind of shadow hunting Nicastro's team was attempting. And in the XME Newton spectrum of that blazar, they found features, absorption features, dips in the spectrum at wavelengths consistent with O7. The fingerprint of hot ionized gas Not in the blazer itself, not in our galaxy, but somewhere in between. Two filaments of it, they concluded, sitting along the line of sight between us and the blazer, absorbing a fraction of its X-ray light and leaving their mark in the spectrum. It was published in Nature. It was talked about widely. And it felt, for a moment, like progress. But the signals were not clean. The statistical significance, the measure of how confident you can be that what you are seeing is real rather than a fluctuation in the noise, was lower than the community would have liked for a claimed detection of something as important as the missing baryons. Other astronomers, looking at the same data with careful eyes, raised questions. Was the OV7 absorption really there, or was it a subtle artifact of the instrument? A ghost in the detector, a feature that looked like a signal but was not? The debate was not resolved quickly. Nicastro's result was real science, done carefully, and it may well have been a genuine detection of warm-hot gas. But it was the kind of result that sits in the literature as suggestive, as consistent with the expectation, rather than as definitive. A hint at the edge of detectability. This is the honest texture of discovery, and it is worth appreciating. The story we tell after the fact, the clean narrative of problem, method, solution, tends to erase the middle period, the years of reaching at something almost within grasp, of publishing results that might be right or might not be, of building a community consensus through evidence that accumulates slowly and uncertainly rather than arriving all at once in a single decisive moment. The missing baryons were not found by one person having a eureka moment. They were approached for decades, from multiple directions by many people, with partial results and contested detections, and slowly growing confidence that the WHIM was really there. Nicastro's 2018 result was part of that long approach. A genuine step forward, just not the closing step. And what closed it, what finally, unambiguously found the missing baryons and weighed them and told us where they lived, came from a direction nobody had anticipated. Not from an X-ray satellite. Not from a radio survey tuned to neutral hydrogen. Not from any instrument designed to hunt the WHIM at all. It came from the most fleeting thing in observational astronomy. A millisecond flash from a distant galaxy. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. It began, as so many genuinely surprising discoveries do, with someone going back through old data. Duncan Lorimer was an astronomer at West Virginia University, a researcher in radio astronomy, the branch of the field that listens to the universe in long wavelengths instead of looking at it in visible light. In 2007, he and his collaborators were examining archival data from the Parkes radio telescope. The data had been recorded 6 years earlier, in 2001, during a survey of the Magellanic Clouds, those two small satellite galaxies that accompany the Milky Way on its long journey through the universe, visible from the southern hemisphere as soft, luminous smudges on a clear night. The survey had done its work, the data had been written to tape, and it had sat in storage while the world went on with other things. The Parkes telescope itself sits in a green valley in rural New South Wales, in inland Australia. It is a magnificent structure, a dish 70 metres across, pointing at the sky on an enormous mount, surrounded by eucalyptus trees and red earth, and a kind of open, patient quiet that seems entirely suited to a place whose job is to listen. In recent years, it has been formally recognized with its Wiradjuri name, Muriang. It is an instrument with a long and celebrated history. It helped relay transmissions from the Apollo 11 moon landing, which is a fact that seems to belong to an entirely different world from the one we are talking about now, but which somehow adds to the sense that this particular dish has been present for a remarkable number of moments. And in 2007, it added another to the list. A student, David Narkovich, was combing through the archival data, applying a search algorithm designed to look for short, dispersed radio pulses, a technique well established in the search for pulsars, those rapidly rotating neutron stars that sweep their beams of radio emission across the sky like cosmic lighthouses. And there, buried in the 2001 recordings, was something unlike any pulsar anybody had ever seen. A single burst, 5 milliseconds long. An incredibly faint trace in the data, but unmistakably there once the algorithm had cleaned up the signal. And it had a property that made it simultaneously convincing and baffling. It was dispersed, smeared across frequency in that very characteristic way, higher frequencies arriving first, lower frequencies arriving later, a smooth sweep that spoke of ionized gas encountered along the way. Every radio astronomer who has ever worked with pulsars recognizes this pattern immediately. The Milky Way's own interstellar medium is full of free electrons, and every pulsar's pulse is dispersed to some degree by those electrons as it crosses the galaxy. The amount of dispersal depends on how many electrons the signal passed through. This is a well-understood, well-measured phenomenon, quantified by something called the dispersion measure, which is essentially a count of the free electrons per unit column along the line of sight. The dispersion measure of the Lorimer burst was enormous, far, far larger than any known pulsar in the Milky Way. So large that if you attributed it entirely to electrons in our own galaxy, you ran out of galaxy long before you had enough electrons to account for it. The math was clear. The signal had crossed far more ionized gas than the Milky Way could reasonably contain in that direction. The source had to be extragalactic, well beyond our galaxy. By the rough relationship between dispersion and distance for a universe of average density, it sat at a cosmological distance, not hundreds of thousands of light-years, like the nearest dwarf galaxies, but potentially billions of light-years. Lorimer published the result in Science in 2007, and the community's reaction was a blend of fascination and careful skepticism that was entirely appropriate. A single burst in archival data with no confirmed host galaxy, no second detection, no theoretical framework that everybody was yet sure about. It was extraordinary if real. But it was one data point. And science builds on one data point only very gingerly. For years, the field lived in that uncertain space. Were there more of these things? Were they real or instrumental artifacts? The Parkes telescope began finding more candidates. And then came the peritons. Peritons, the name comes from a mythological creature, a winged stag from medieval bestiaries, which some astronomer with a poetic inclination decided was the right name for a mysterious, apparently supernatural signal that kept turning up in the Parkes data. These periton signals looked, at first glance, disturbingly similar to the kind of dispersed burst you might expect from a real astrophysical source. They were dispersed across frequency. They had structure. But something was wrong with them. They did not behave quite like a source at a fixed point in the sky should behave, and they appeared too frequently, from too many directions, to plausibly all be genuine cosmological events. For years, peritons muddied the waters. They were real signals, not random noise. But were they the same thing as the Lorimer burst? or something else? The uncertainty was corrosive. If you couldn't trust your instrument to tell the difference between real astrophysical bursts and whatever peritons were, how could you build a science on the bursts? The answer came in 2015. Emily Petrov and her collaborators set up a radio frequency interference monitor at the Parkes site, essentially a device designed to track the ordinary electromagnetic noise of the local environment. And they watched, and they waited. And one day a periton appeared in the telescope data at exactly the same moment as a specific interference signature in the monitor. They tracked it down. The source of the periton was a microwave oven on the telescope site. Specifically, a microwave oven whose door was being opened before the timer had finished, interrupting the magnetron mid-cycle, releasing a brief pulse of microwave frequency radiation that, under just the right conditions, was leaking out and being picked up by the sensitive receiver on the great dish. Years of ambiguity, resolved by lunch. It is a story that the history of astronomy will tell for a long time. Because it has everything. The mysterious signal, the painstaking detective work, and the wonderfully mundane culprit. A microwave oven. On the same site as one of the most important radio telescopes in the world, quietly generating fake cosmic signals every time someone got impatient with their leftovers. But here is the thing. The resolution of the periton mystery was not a setback for the fast radio burst field. It was the opposite. Because once you knew what peritons were and how to recognize them, you could confidently set them aside. And what remained, the signals that were not peritons, that genuinely survived all the tests for being real astrophysical bursts, stood out with new clarity. The real fast radio bursts were real, unambiguously, verifiably, genuinely coming from the cosmos. And the cosmos, it was becoming clear, was producing them in extraordinary numbers. A fast radio burst. Let's stay with that name for a moment and let it become concrete. Because in popular coverage, these things are sometimes described in ways that emphasize their mysteriousness, strange signals from space, unexplained flashes, something we don't understand, in a way that makes them sound either threatening or tantalizing in an alien contact kind of way. And the truth is simultaneously more grounded and more astonishing than any of that. There is no serious scientific consideration of fast radio bursts as evidence of alien technology. Every studied burst is consistent with natural astrophysical processes. What makes them astonishing is not their inexplicability, but their nature. What they are, in plain terms, is this: a flash of radio waves, a few milliseconds long in most cases, arriving from a distant galaxy, and carrying, in those few milliseconds, a quantity of energy that is genuinely difficult to hold in your mind comfortably. We should stay with the energy for a moment, because it matters for everything that comes next. It is the energy that makes an effective probe of the universe it crossed. And it is the energy that, even knowing the physical mechanism responsible for producing it, remains something of an awe-inducing figure. In the few milliseconds of a fast radio burst, in the radio frequency band alone, not counting any other wavelengths, the burst releases somewhere in the range of 10 to the 32nd to 10 to the 33rd joules of energy. Those numbers are abstract, so let us put them alongside something familiar. The sun, our sun, which has been shining for 4.5 billion years and will shine for another 5 billion or so, generates its energy by fusing hydrogen into helium in its core. Every second it releases about 4 times 10 to the 26th joules. It does this around the clock, without pause, in every second of every day since before the Earth existed. A fast radio burst, in a few thousandths of a second, releases in radio waves alone an amount of energy comparable to what the Sun emits. Across all wavelengths, in somewhere between several days and a week, not over the course of a year, not over a century, several days, in a few thousandths of a second, from a galaxy that is, in some cases, literally billions of light years away. And yet the burst still arrives here, at Earth, with enough power to be detected by a radio telescope. To trip a sensor, to write a bright spike into a recording, to be found by a student going through archival data and to announce itself 6 years late as something the universe was doing all along and had simply not yet been noticed. There is something quietly vertiginous about that image. The burst leaving its source, perhaps 8 billion years ago, before the Sun existed, before the solar system had condensed from its nebula, before the Earth was anything more than diffuse gas, and making its slow crossing of an almost incomprehensibly large universe, and still, at the end of all that time and all that distance, being bright enough to set off an alarm. Whatever is making these things, it is not subtle, and the brightness matters, because brightness is what makes an verb useful, what makes it a probe rather than merely a spectacle. Because as that flash travels across billions of light years, across all that gas, all that invisible million-degree tenuous plasma that the simulations said was out there and that XM Newton could barely glimpse, the gas is doing something to it, leaving a mark on it, writing into the signal itself a hidden record of everything it crossed, a count of every free electron in its path. And reading that count, understanding how it works and what it tells us, that is the mechanism that finally located the missing half of the universe. That is the story the flash was carrying all along, waiting for us to learn how to read it. But we will get to that. There is time. No rush at all. The signal is still crossing its billions of light years. The electrons are still doing their work. And we can rest here for a while, with the image of that distant flash and the knowledge that hidden inside it, encoded in a delay so slight it takes a precise instrument to measure, is the answer to a question that kept the finest cosmological minds occupied for decades. Rest if you want to. Drift if you are inclined. The burst will still be arriving when you are ready. So, let's talk about what is actually making them. Because that question, what produces a fast radio burst, what engine sits at the heart of a flash, that brief and that powerful, occupied radio astronomers for nearly a decade after the Lorimer burst turned up in those archived Parkes recordings in 2007. And the answer, when it finally arrived, came not from a new telescope or a new theory, but from a burst that decided to repeat itself. Most fast radio bursts, as far as anyone can tell, are one-offs. A single flash arriving from a particular patch of sky, and then nothing, no encore, no echo. Just the one extraordinary event, and then silence. Which made them difficult to study in any systematic way, because you can't point a follow-up telescope at a source that has already finished emitting. You get one look, in one direction, in one fraction of a second, and then the opportunity is gone. But in 2012, though the significance wouldn't be clear for a while, a burst arrived from a source that was apparently not finished. It came in again. And again after that. This was FARB 121102. The numbers are simply a date code. The burst was first recorded in November 2012, but the object it pointed to would become one of the most studied single sources in radio astronomy, because for the first time, a fast radio burst was repeating, coming back, giving astronomers the chance to stare at one spot in the sky for hours and days at a time, waiting for the next flash, building up a catalogue of emissions from a single location rather than chasing random one-time events across the entire dome of the sky. And with a repeating source, you could do something that had been impossible before. You could localize it, not just roughly, not just somewhere in that general direction, but precisely. Precisely enough to say, this burst is coming from that galaxy, that specific galaxy, right there. And the galaxy in question turned out to be a small, faint, irregular dwarf galaxy sitting roughly 3 billion light-years away. 3 billion. Not a neighbor, not something in our cosmic backyard. A galaxy so distant that the light we see from it left before the Earth had finished forming its oceans. The localization was published in 2017 by a collaboration led by Shami Chatterjee, with Sriharsh Tendulkar and others involved in nailing down the host galaxy. And the result mattered for reasons beyond mere curiosity about where the burst came from. It mattered because it demonstrated for the first time that fast radio bursts were definitively extragalactic. Not just probably, not just apparently, but demonstrably, measurably, observationally, coming from billions of light-years away. The distance question was settled, and with distance confirmed, the energetics became even more staggering. Because if you know how far away something is, and you know how bright it appears from here, you can calculate how intrinsically luminous it must actually be. And the numbers for FARB 21102 were extraordinary. Each individual burst releasing, in its milliseconds of existence, energy comparable to what the sun radiates over the course of entire days. Not years, days, from a single millisecond flash. Whatever was making this thing was operating at a scale of physics that doesn't exist anywhere in our ordinary experience. But here's where the story gets strange, because even with a repeating source, even with a confirmed host galaxy, the question of the engine, the actual mechanism producing the bursts, remained open. Theories multiplied. Some of them were quite reasonable, invoking known and well-understood classes of astrophysical objects. Others were considerably more exotic. A few ventured into territory that the popular press, with perhaps understandable enthusiasm, began describing in terms that had nothing to do with astrophysics at all. We'll come back to that. Briefly. But first, the answer. Or at least, the answer that the evidence now strongly supports for a large fraction of fast radio bursts, and possibly for all of them. It involves an object called a magnetar. And if you've never heard of a magnetar, rest easy for a moment and let this settle in, because it is one of the stranger things the universe makes. A magnetar is a type of neutron star, and a neutron star is already extraordinary enough on its own terms. It is what you get when a massive star, far more massive than our Sun, exhausts its nuclear fuel and collapses. The outer layers explode outward in a supernova, and the core is crushed inward under gravity so intense that the protons and electrons are squeezed together into neutrons. The result is an object roughly 10 to 15 kilometers across, small enough, in principle, to fit within a city, but containing the mass of a star. A teaspoon of neutron star material would weigh, on Earth, several 100 million tons. The density is near nuclear. The gravity at the surface is roughly 200 billion times what you feel sitting wherever you're sitting right now. A magnetar is a neutron star that, on top of all of that, has an extraordinarily powerful magnetic field, the strongest magnetic field of any known object in the universe. We're talking about fields 1,000,000,000,000 times stronger than Earth's and 1,000 times stronger than an ordinary neutron star. Fields so intense they distort the very structure of atoms near the surface, stretching electron clouds into thin cylinders. Fields that, if a magnetar somehow materialized halfway to the moon, would erase every credit card and disrupt the iron in your blood from that distance. They are not gentle objects. And every so often, for reasons still being worked out in detail, a magnetar releases a burst of energy. A starquake, perhaps, in its iron crystalline crust, releasing stress that has built up in those unimaginably powerful magnetic fields. Or a sudden rearrangement of those fields themselves, like a rubber band that has been wound too tight and suddenly snaps. Whatever the precise trigger, the result is a pulse of electromagnetic radiation, including, it turns out, radio waves. The definitive link between magnetars and fast radio bursts arrived in April 2020, and it came from the most convincing possible source, our own galaxy. The magnetar in question is called SCAR 1935 plus 2154. SCAR stands for soft gamma repeater, which is one of the classes of objects magnetars are known to produce, and 1935 plus 214 simply indicates its coordinates in the sky. It sits inside the Milky Way, in a region of our galaxy roughly 30,000 light-years from Earth. And in April 2020, it did something that made two separate radio telescopes on two separate continents light up at almost exactly the same moment. It produced a fast radio burst. The burst is designated FARB 20428 after its detection date, and unlike every other FIRB ever found, this one had an unambiguous, confirmed source, a known magnetar inside our own galaxy, caught in the act. The burst was detected by the WHIM telescope in Canada and separately confirmed by an instrument called STARE-2 in the United States. The two independent detections, the known distance, the known source, the timing, all of it converged on a single conclusion that the field had been waiting 13 years to reach. Magnetars make fast radio bursts. Now, and this is an important caveat that the data genuinely supports, it doesn't necessarily mean that all fast radio bursts are made by magnetars in exactly the same way. The universe is inventive. There may be other engines for other bursts, particularly for the most extreme, most energetic events. But the April 2020 detection removed the most frustrating uncertainty, the existence of at least one plausible, physically well-motivated mechanism was no longer a matter of theory. It was an observation, and with that settled, at least in outline, the field was free to focus on what mattered most for the missing baryon problem. Not what makes the flash, but what the flash does on its way to us. But before we get to the mechanism, and we will, very soon, and it is the most satisfying piece of this whole story, let me tell you a small, slightly embarrassing chapter in the history of FIRB science. Because not everything that looked like a fast radio burst turned out to be one. For several years after the Lorimer burst was announced, a particular class of signals kept turning up in data from the Parkes radio telescope in Australia. They were called peritons, a name borrowed, with a certain wry humour, from a mythological winged deer. The kind of name you give something when you're not quite sure what it is. Peritons looked, in some ways, like fast radio bursts. They had a frequency-dependent dispersion. They were brief. They arrived with a sort of cosmic authority. And they were maddening, because they showed up intermittently and couldn't quite be explained. For a while, some researchers worried that peritons and fast radio bursts might be related, or that peritons might indicate some local interference phenomenon that could cast doubt on the reality of the FRBs themselves. The truth, when it arrived in 2015, was considerably more mundane. The peritons were coming from the on-site microwave oven. Specifically, from the microwave oven in the staff room near the telescope when someone opened the door before the timer had finished. The microwave emits a pulse of radio frequency energy when the door interrupts its cycle at precisely the wrong moment, and the telescope, sensitive enough to detect signals from billions of light-years away, was also quite capable of detecting a microwave oven 40 meters distant. Once the source was identified, it took very little time to confirm. Staff members deliberately replicated the behavior, opened the microwave early, at different power settings and different timings, and sure enough, there were the peritons appearing in the data right on cue. Traced to a kitchen appliance. Published, with what must have been a mix of relief and sheepishness, by Emily Petroff and collaborators in 2015. It is, if nothing else, a reminder that sensitive instruments pick up everything, and that science proceeds by the laborious elimination of all the ways you might be fooling yourself. The peritons were eliminated. The real fast radio bursts were not. And the distinction once made only reinforced the genuinely cosmic nature of the signals that remained. There are a great many of them. The WHIM telescope, the Canadian Hydrogen Intensity Mapping Experiment, a fixed array of cylindrical reflectors in the Okanagan Valley of British Columbia, began its systematic survey of the sky for fast radio bursts around 2018. And what it found over the following years was that FRBs are not rare events at all. Not in the sense of being genuinely uncommon in the universe. They're only hard to catch because each one arrives in a single millisecond from an unknown direction, and catching them requires essentially the right telescope pointed at the right patch of sky at exactly the right fraction of a second. WHIM, with its wide field of view and its continuous monitoring, began catching them by the hundreds. Its first catalogue, published in 2021, contained hundreds of individual bursts from dozens of distinct sources, and estimates based on the detection rate extrapolated across the portions of the sky the telescope wasn't watching at any given moment. Suggested that something on the order of 1,000 fast radio bursts were arriving from across the entire sky every single day. Every day. Not every year. Every day. Most of them arriving unseen, washing over the Earth, passing through buildings and bodies and the ionosphere with the same indifference they pass through everything else in the universe. 1,000 cosmic dipsticks falling on deaf antennae, their hidden records of the intergalactic medium unread, but some of them landing on WHIM or on the Australian Square Kilometre Array Pathfinder, ASCAP, or on one of the other instruments joining the search. Caught, recorded, processed, and slowly the catalogue grew. Which brings us, finally, to the mechanism. To the thing that turns a fast radio burst from a spectacular but baffling astrophysical event into the most precise measuring instrument ever pointed at the diffuse universe. It starts with a simple property of radio waves, one that physicists have understood for well over a century, but whose cosmological implications only became fully apparent when the bursts arrived to exploit them. Radio waves, like all electromagnetic radiation, travel through a vacuum at the speed of light. All of them, regardless of their frequency. A high-frequency radio wave and a low-frequency radio wave in empty space race each other perfectly, arriving at the same moment, always, no matter the distance travelled. But the universe is not quite empty. There are electrons out there. free electrons, not attached to atoms, just drifting individually through the plasma of the intergalactic medium, the gas of galaxy halos, the thin ionized atmosphere of the Milky Way. Not many of them. The density of the intergalactic medium is extraordinarily low, on the order of 1 electron per cubic meter in the most diffuse regions, which makes the best vacuum a laboratory can produce here on Earth seem almost crowded by comparison. But there are a lot of cubic meters between here and a distant galaxy. And free electrons do something to radio waves. When a radio wave passes through a region containing free electrons, the electrons respond to it, they're charged particles. And electromagnetic waves are oscillating electric and magnetic fields, so the interaction is unavoidable. The electrons slow the wave down, ever so slightly. Not much, an almost imperceptible slowing. But the crucial detail is that the slowing depends on frequency. Low-frequency radio waves are slowed more than high-frequency ones. Higher frequencies are barely affected, they plough through almost as quickly as they would through empty space. Lower frequencies are held back a little longer. The result, for a pulse that begins as a sharp simultaneous flash of many frequencies at once, is that it arrives at the far end, smeared apart in time. The high-frequency components, the higher notes, if you want to think of it musically, arrive first. The low-frequency components, the bass, arrive a little later, not by much, in absolute terms, but by a measurable amount, and precisely measurable at that. Think of it this way. Imagine you have a deck of cards, and you throw them all forward at the same moment, in the same direction. If they're all exactly the same size and shape and weight, they'll all travel the same distance in the same time. But if, for some reason, the red cards are ever so slightly lighter than the black cards, and they're being thrown through a very thin mist that affects lighter things more, then after a long enough journey, the red cards will have pulled slightly ahead of the black ones. By the time the deck arrives at the far end of a football field or a continent, the two colours have separated, and by measuring how far apart they've spread, you can calculate how dense the mist was. That separation, that smearing of the radio pulse in time, from a clean, sharp spike to a swept, frequency-dependent arrival, is called dispersion. And the quantity that describes how much the pulse has been smeared is called the dispersion measure, or DM. The dispersion measure is not complicated in its essence. It is simply proportional to the total number of free electrons along the entire path the pulse travelled, what physicists call the electron column density. More electrons crossed equals a larger dispersion measure equals more smearing. The relationship is precise enough that it's been written down as a formula, one that radio astronomers use routinely. The delay in arrival time between two radio frequencies is approximately 4.15 milliseconds, multiplied by the dispersion measure, multiplied by 1 over the square of the lower frequency minus 1 over the square of the higher frequency, with frequency measured in gigahertz and the dispersion measure in units called parsecs per cubic centimeter. That formula is the cosmic dipstick. Because what it means in practice is this: you detect a fast radio burst. You measure with extraordinary precision, because radio telescopes are extraordinarily precise instruments, how much earlier the high frequencies arrived compared to the low frequencies. You plug that timing difference into the dispersion formula. Out comes the dispersion measure. And the dispersion measure tells you how many free electrons the pulse crossed on its entire journey. Every single free electron. In the Milky Way, in the halos of intervening galaxies, in the million-degree tenuous filaments of the Warm-Hot Intergalactic Medium, everywhere, The flash doesn't care whether the electrons it encountered were in a hot region or a cold one, whether they were in dense gas or thin gas, whether they were in a place that any optical or X-ray telescope could hope to see. An electron is an electron. If it was free and the flash passed through it, it registered in the dispersion measure. This is the key thing that makes FRBs different from every other probe astronomers had tried. The Warm-Hot Intergalactic Medium, all that million-degree, ultra-thin gas strung along the cosmic web's filaments, the gas that Sen and Ostriker and Dav's simulations predicted in the late 1990s, and that XME Newton could only barely hint at, that gas is made of ionized plasma. It is, by definition, a sea of free electrons. And those electrons don't care that no X-ray telescope can see them efficiently. They don't care that they're too hot for neutral hydrogen surveys and too diffuse for conventional X-ray imaging. When a fast radio burst passes through them, they slow its lower frequencies and let its higher ones race ahead, and that tiny, measurable delay is as good as a census taker's tally, every one of them counted. None of them invisible to this particular instrument. That is why the flash worked when everything else had only partially succeeded. Not because it was louder or more energetic or aimed at the right kind of wavelength, but because the mechanism of dispersion is indifferent to exactly the properties, temperature, density, emission brightness. That made the WHIM invisible to everything else. Now, before the missing baryon problem could be solved using this tool, astronomers needed to do something that seems obvious, but turned out to be genuinely difficult. They needed to understand the dispersion measure well enough to subtract out all the contributions that weren't from the intergalactic medium. Because UNFERB's total dispersion measure isn't purely a count of intergalactic electrons, it's a sum of several distinct contributions layered one on top of another throughout the burst's journey. Start from the burst's origin. The host galaxy, the galaxy where the magnetar lives, contains its own gas. Star-forming regions, the galaxy's disk, the galaxy's own halo, all of that adds electrons to the dispersion measure before the burst has even left its birthplace. Then comes the vast journey through intergalactic space, the piece astronomers actually want to measure, the one that counts the diffuse gas of the cosmic web. But then, as the burst approaches us, it passes through the halo of the Milky Way, our own galaxy's extended gaseous atmosphere, stretching well beyond the visible disk. And finally, the burst crosses the disk of the Milky Way itself, through all the ionized gas in our own galactic neighborhood. By the time the burst reaches your radio telescope, its dispersion measure reflects the sum of all four of those components: host galaxy, intergalactic medium, Milky Way halo, and Milky Way disk. To isolate the piece you want, the intergalactic medium, where the missing baryons live, you have to subtract the other three. The Milky Way disk contribution is the best understood. Radio astronomers have been mapping our galaxy's electron distribution for decades using pulsars as probes. Pulsars, rapidly rotating neutron stars that beam radio waves toward Earth as they spin. Creating regular pulses like a cosmic lighthouse were the original demonstration that dispersion measure could be used to map electrons. Because pulsars are inside the Milky Way, at known distances, their dispersion measures built up a three-dimensional map of our galaxy's ionized gas. Two major models, called NE 2001 and YMW16, after the names of their authors, Cordes and Lazio for NE 2001. Manchester, and Wang for YMW16 encode that knowledge in software. Point any direction in the sky, Specify a distance, and they'll give you a predicted Milky Way disk contribution to subtract. The Milky Way's halo is less well characterized, but estimates exist and can be modeled. The host galaxy contribution is the awkward one. You can't directly measure it, you can only model it statistically, averaging over many different types of host galaxies seen at different orientations, and accept that for any individual burst there's an uncertainty. But with enough bursts in a sample, the host galaxy contributions average out over the population. Which means the critical remaining ingredient, the one that separates a dispersion measurement from an actual statement about the intergalactic medium, is knowing the distance to each burst. And here is where the problem gets subtle. The dispersion measure alone doesn't tell you the distance. If you measure, say, a dispersion measure of 800 parsecs per cubic centimetre for a given burst, that could mean you're looking at a relatively nearby burst that crossed dense gas, or a very distant burst that crossed thin gas over a much longer path. The DM is a product of density and distance integrated together. To turn it into a measurement of the average density of the universe, and then from that into a baryon count, you need to know the distance independently. And the distance to a fast radio burst means its redshift. How much has the universe expanded since the light, the radio waves, left their source? That's redshift. And redshift requires spectra. And spectra require knowing which galaxy the burst came from. And knowing which galaxy the burst came from requires localizing the burst well enough to point an optical telescope at it and find the host galaxy among the many faint smudges of light in that direction. Localization, that was the unsung technical bottleneck. A single-dish radio telescope, like the original Parkes dish, Murayang, can tell you that a burst arrived from a broad patch of sky, perhaps half a degree wide, which sounds small, but corresponds to an area containing potentially thousands of faint galaxies. You can't identify the host from that. You need a radio interferometer, an array of antennas spread across a wide baseline, whose signals are combined to synthesize a much sharper angular resolution, narrow enough to pinpoint a location in the sky to arcsecond precision. That is where instruments like ASCAP, the Australian Square Kilometre Array Pathfinder, became decisive. ASCAP is an interferometric array. Its antennas spread across a large enough baseline that it can localize a fast radio burst to within a fraction of an arcsecond on the sky. Precise enough to point a large optical telescope, the kind with a mirror several meters across, at exactly the right spot and find the host galaxy. Measure its spectrum, determine its redshift, get the distance. Similar capabilities exist in the VLA, the Carl G. Jansky Very Large Array in New Mexico, with its Y-shaped array of 27 radio dishes spread across the desert. And in Meerkat, the South African array of 64 dishes, and in the DSA 110, the Deep Synoptic Array, 110 dishes in the Owens Valley of California, specifically designed and optimized for FREB localization. Each of these instruments takes a different approach to the same engineering challenge, catching a millisecond flash in real time and preserving enough spatial information to say, to arcsecond accuracy, where it came from. Getting that right is genuinely hard. A burst lasts a millisecond. You don't know when it's coming or from which direction. You need to be continuously recording data from wide patches of sky at high time resolution. And you need processing pipelines fast enough to identify the event in near real time and save the raw voltage data before it's overwritten. This is not a matter of simply pointing a telescope and waiting. It's a matter of building the entire data acquisition and processing infrastructure around the requirement that nothing interesting can happen without you catching it. For the first decade of FIRB science, most bursts were detected but not localized. Their dispersion measures were measured, their structures analyzed, their energy distributions catalogued, but without distances, they could not be used as dipsticks for the baryon budget. They were spectacular in isolation, but not yet calibrated. FIRB 121102, the repeater, changed that for a single source, as we mentioned. But a repeating source is somewhat unusual, and localizing it required a different approach. Training radio interferometers at a known position and waiting for the next burst. That works once you know where to look. But the one-off bursts, the ones that appear from a new direction every time, without warning, needed a different solution. ASCAP provided it. By recording data from a wide field of view, ASCAP could catch one-off bursts and retain the spatial information needed to localize them after the fact, once the search algorithms flagged the event. Not immediately, the pipeline had to be built, but it worked. And with working localization came the first samples of fast radio bursts with confirmed host galaxies and measured redshifts. The dispersion measure for each burst, the redshift for each burst, subtract the known Milky Way contributions, average over the unknown host contributions, and what remained was a measurement for each burst of the electron content of the intergalactic medium along that particular sightline. Do that for several bursts at different distances, different redshifts, different directions on the sky. And you can ask, does the dispersion measure rise with redshift the way it should if the intergalactic medium contains the predicted quantity of baryons? If the baryons were all there, all along, strung along those million-degree filaments, the answer would be yes. The DM would grow with redshift in a particular way, tracing out what became known as the Macquart relation, named in tribute, after the Australian radio astronomer Jean-Pierre Macquart, who was one of the key architects of the theoretical framework and who died in 2020. The same year the landmark result bearing his name was published, and the answer was yes. But that is the story of Part 4. Which is coming. Rest now. Let the electrons drift, let the filaments extend through the dark between galaxies, patient and invisible and full of atoms. The burst has crossed 8 billion light-years to reach us, carrying its hidden count in the shape of its smeared arrival, and we are almost ready to read it. Somewhere in your own body, in the calcium in your teeth, in the iron in your blood, in the carbon woven through every cell. There are atoms that were forged in stars that lived and died long before this solar system existed. Those atoms spent billions of years in the kind of diffuse intergalactic gas the dispersion measure counts. They drifted in those invisible million-degree filaments, part of the missing inventory, before gravity gathered them into a new generation of stars, and eventually into a planet, and eventually into you. The missing baryons were never really missing from the universe. They were missing from the map, and a millisecond flash, smeared by electrons across a handful of frequencies, drew the map. So, let's read it. In 2020, a team of astronomers working with the Australian Square Kilometre Array Pathfinder, ASCAP, that grid of dishes in the remote Western Australian outback, published a paper in the journal Nature. The lead author was Jean-Pierre Macquart, and the title was direct, almost quietly confident, a census of baryons in the universe from localized fast radio bursts. A census. The word itself is almost domestic. You picture someone going door to door, clipboard in hand, counting heads. That is, in a way, exactly what they did. Except the doors were galaxies, and the clipboard was a radio telescope. And the counting was done not by looking at anything directly, but by measuring how long it took a millisecond flash to arrive, and by how much the flash had been smeared. They used 5 bursts, just 5 fast radio bursts that a SCAP had not only detected but localized, pinned precisely enough in the sky that follow-up observations with optical telescopes could identify the host galaxy, measure its redshift, and establish the distance. 5 flashes from 5 different galaxies at 5 different distances, each one carrying in the shape of its smeared arrival a count of every free electron it had crossed on its way to us. And when those 5 dispersion measures were plotted against their distances, when the smear was compared to the redshift, the points fell along a line, a clean, rising line. The farther the burst, the higher the dispersion measure. More distance crossed, more electrons encountered, more smearing. And the slope of that line, the rate at which dispersion measure grew with distance, matched the prediction. It matched what you would expect to see if the total baryon content of the universe, as fixed by Big Bang Nucleosynthesis and confirmed by the cosmic microwave background, was really there, really present, spread across the diffuse intergalactic medium. The baryons weren't missing. They had been there the whole time, in the gas between the galaxies, too thin and too hot and too spread out for X-ray telescopes to weigh reliably, invisible to optical surveys, absent from every map because no instrument had been able to count them directly. Until a millisecond flash did it for us. The relationship those 5 bursts traced is now called the McCourt relation. Jean-Pierre McCourt died in May of 2020, just months after the paper was published. He was 50 years old. The relation bearing his name is now one of the foundational tools of observational cosmology, a kind of cosmic ruler built not from light in the usual sense, but from delay, from smear, from the gap between when the high notes arrived and when the low ones caught up. 5 bursts, decades of searching, and the answer written in the shape of the signal itself. Take a breath. There's no rush. If you're still with me, wonderful. If you're drifting, that's wonderful too. The universe will still be here. Now, if you're the kind of person who finds a single paper with 5 data points slightly tantalizing, if you're thinking, that's suggestive, but is it solid, then you're thinking like an astronomer. 5 localized FRBs is a proof of concept. It's enough to say the mechanism works, the baryons appear to be there. It is not enough to say we've mapped every last wisp of intergalactic gas across all of cosmic time, which is exactly why the work continued. Enter Shannon Ryder and a burst called FARB 2206 WHIM-0A. In 2023, Ryder and collaborators published a paper in the journal Science describing what was at the time the most distant, most energetic, well-localized fast radio burst ever detected. FARB 2206 WHIM-A came from a galaxy at redshift roughly 1. That number, redshift 1, is worth sitting with for a moment. It means the universe, when that burst was emitted, was about half the size it is today. The light, or rather the radio waves, from that burst had been travelling for approximately 8 billion years before reaching the escape dishes in Western Australia. 8 billion years. The Earth didn't exist yet when that burst left its source. The sun hadn't formed. The atoms in your body were scattered across different stars, different nebulae, in different configurations entirely. And that burst, that flash, lasting a few milliseconds, crossed 8 billion years of intergalactic gas and arrived smeared in a very particular way, and the smear told us something. It told us the McCourt relation holds, not just in the local universe, not just for the past few billion years, but across most of cosmic history. The baryons were out there then, too, in the filaments, in the warm-hot intergalactic medium, strung across the cosmic web, in the right quantity. The census wasn't just confirmed at one time and place. It was confirmed across the arc of cosmic time itself. And then there was FARB 18112. This one is slightly different in flavor. In 2019, a team led by J. Xavier Prochaska used a single localized fast radio burst, FARB 18112, in an unusual way. The burst, as it traveled to us, happened to pass very close to the line of sight through the halo of a foreground galaxy. Not through the galaxy itself, but through its extended gaseous atmosphere. The circumgalactic medium, that vast envelope of warm gas that surrounds galaxies like an atmosphere, surrounds a planet, only much, much larger and far thinner. And FARB 1811112 threaded right through it. Prochaska and the team published the result in the journal Science that same year. What they found was surprising and quietly beautiful. The halo gas was there, the dispersion measure picked it up. But it was calm, remarkably calm. The magnetization was weak, the turbulence was low. Whatever processes had pushed gas out of the galaxy, supernovae, the winds from black holes, all the violent stellar feedback that modern cosmological simulations argue about, the halo at that particular moment in that particular galaxy was serene. And FARB had X-rayed the invisible atmosphere of a distant galaxy the way you'd X-ray a patient, not destructively, just by passing through and leaving a record. The gas that no optical telescope could see, too diffuse and too extended for conventional imaging, was revealed by the shape of a millisecond flash. One burst. One galaxy halo. Seen from 8 billion light-years away in radio waves by measuring a delay of fractions of a second. There's something almost tender about it. The universe, patient and enormous, and mostly empty, carrying atoms in gas so thin you could pass your hand through it without knowing, and a flash, shorter than a heartbeat, as energetic as the sun is in days, reading every one of them as it goes. But the most complete reckoning came more recently still. In 2025, a team led by Liam Connor published a paper in Nature Astronomy using a larger sample of localized fast radio bursts gathered with the Deep Synoptic Array, DSA 110, a collection of antennas in the Owens Valley of California, combined with observations from other instruments. And instead of simply confirming that the total baryon budget matched the prediction, they did something more ambitious. They tried to partition the budget. To say not just the baryons are there, but and here is where they are, specifically, the result, and these are best estimates, with real uncertainty attached, as all good science should be, came out roughly like this. About 3/4 of all ordinary matter, roughly 76%, lives in the diffuse intergalactic medium. Not in galaxies, not in galaxy clusters, not in the spectacular filaments you can image directly. In the diffuse gas between everything, the warm-hot intergalactic medium, the WHIM, the stuff that Sen and Ostraika and Dav and their colleagues predicted in simulations a quarter-century ago, the stuff that sat in the detection blind spot, too hot for hydrogen surveys, too thin and too cool for X-ray telescopes to reliably weigh. About 15% lives in the extended halos around galaxies. That circumgalactic medium, the invisible atmospheric envelope that FARB 18112 so quietly probed. And the rest. The remaining fraction. Roughly 9%, give or take. That's what lives inside galaxies themselves, in the stars, in the planets, in the cold molecular clouds, in everything we can actually see and point a telescope at directly. 9%. Think about that for a moment. Everything you have ever seen in a photograph of the night sky, every galaxy, every nebula, every star cluster, every spiral arm, every galaxy's worth of light across billions of light years. All of that visible, luminous, structured content is made of roughly 9% of the universe's ordinary matter. The rest is invisible, diffuse, floating in the dark between them. The empty-looking cosmos holds most of the atoms. It's the kind of fact that takes a moment to settle. We think of space as emptiness, as the gap between the real things, the stuff that matters, the galaxies and stars and planets and everything we build stories around. And it turns out the gap is the inventory. The void is where the atoms live. Most of them. 3 out of 4. This is the satisfying inversion at the heart of the missing baryon problem, and it's the one most popular accounts of the story never quite reach. They stop at the matter was missing. They stop at fast radio bursts are mysterious. The story doesn't stop there. The story ends here, with a partition, with percentages, with the census finally closed. Or at least closed well enough to say, we know where the atoms are. They are in the intergalactic medium, in the cosmic web, in the filaments of that vast and intricate large-scale structure that stretches across hundreds of millions of light years. Let's stay with the cosmic web for a moment, because it's worth picturing slowly if you could step back, impossibly far back. Far enough to see the universe not as individual galaxies, but as a pattern. What you would see is something that looks, a little, like a vast three-dimensional web. Or foam. Or the inside of a sponge. Matter, both dark matter and ordinary baryonic matter, following the same gravitational blueprint, has arranged itself into sheets and filaments. Long threads of gas and galaxies meeting at dense nodes, which are the massive galaxy clusters where thousands of galaxies pile together under enormous gravity. And between the filaments, voids. Nearly empty bubbles of space, sometimes hundreds of millions of light years across, where almost nothing lives. This is the large-scale structure of the universe. The cosmic web. And the baryons, the ordinary matter, your baryons, my baryons, trace those filaments. Not in the dense nodes, not primarily in the galaxies, along the threads themselves, in gas so tenuous that a cubic meter of it contains only a handful of particles. The filaments extend for hundreds of millions of light years. And there are so many of them, and they are so vast, that all that thin gas adds up to most of the mass of ordinary matter in the universe. The cosmic web is not primarily visible. It's not primarily luminous. What we see, the galaxy surveys that map the universe by plotting the positions of hundreds of thousands of galaxies, is, in a sense, just the scaffolding, the glitter at the intersections. The real content, by mass, is the gas in the spaces between. And before fast radio bursts arrived as a tool, getting at that gas was genuinely difficult. We had indirect methods. One of them worth mentioning is the thermal Sunyaev-Zeldovich effect, a subtle distortion that hot gas imprints on the cosmic microwave background as CMB photons pass through it. In 2019, 2 independent teams, de Graaf and collaborators, and Tanimura and collaborators, used this effect, stacking the signal between many pairs of galaxies to reveal warm gas bridging them. The signal was there. It was consistent with warm filamentary material connecting galaxies across millions of light years. It was corroborating evidence, real, careful, indirect evidence, but model-dependent. You needed to assume things about the geometry of the gas, the temperature distribution, the line of sight. The Sunyaev-Zeldovich stacking technique was pointing at the right answer. It just couldn't deliver the precision the census required. What the fast radio bursts delivered was something more direct. A photon, or rather a pulse of photons, smeared by electrons across a radio band, doesn't care about temperature. Dispersion measure counts free electrons. Full stop. Whether the gas is 100,000 degrees or 10 million degrees, whether it's turbulent or calm, whether it's in a dense knot or spread across 50 megaparsecs of filament, if it has free electrons. They contribute to the delay, they add to the measure, they are counted. That universality is the key. It's what makes the dispersion measure such a clean instrument for this specific problem. The WHIM's defining inconvenience, that it's too hot for some telescopes and too thin for others, simply doesn't affect an FIRB. The flash doesn't notice. It crosses a 1,000,000-degree filament the same way it crosses a cold, dense cloud, accumulating delay proportional to the electrons, indifferent to everything else. And now there are hundreds of localized FRBs. WHIM, the Canadian Hydrogen Intensity Mapping Experiment, has catalogued bursts in their hundreds, heading toward thousands. The Deep Synoptic Array, the Australian Square Kilometre Array Pathfinder, the VLAR, Meerkat in South Africa, all of them finding bursts and increasingly often localizing them. Each new localized burst is another data point on the Mach-Watt relation, another measurement of the intergalactic medium, another photon smeared by invisible gas that it found for us, and the future of this tool is genuinely wide. Because what a fast radio burst measures isn't only the quantity of electrons, it also measures, via a related effect called Faraday rotation, the rotation of the polarization angle of the radio wave as it passes through magnetized plasma, the magnetic fields threading the intergalactic medium. Those magnetic fields are among the most poorly understood features of the large-scale universe. How strong are they? Where did they come from? Were they seeded in the very early universe or amplified by galaxies over billions of years? FRBs, used carefully, can begin to answer those questions. They can also measure the universe's expansion. Because the Mach-Watt relation connects dispersion measure to redshift, to distance, and because that connection depends on how many electrons a given volume of space contains, and because that density changes as the universe expands, FRBs become, in principle, an independent way to measure the Hubble constant. The expansion rate, one of the most contentious numbers in modern cosmology, where two families of measurement disagree at a level that may signal new physics. FRBs don't yet have the precision to settle that debate, but the path is being built. They can probe how galaxies interact with the intergalactic medium, how much gas gets blown out of galaxies by the stellar winds and supernovae and black hole activity that cosmologists call feedback, how that gas distributes itself in halos, whether it cycles back in. The circumgalactic medium is a battleground in our understanding of how galaxies form and evolve, and fast radio bursts are becoming one of its most precise probes. A millisecond flash, and the whole universe becomes slightly less dark. Wherever you are right now, if you're still awake, quietly listening, or if you're balanced somewhere on the soft edge of sleep, take a moment, if you would, to think about where you actually are in all of this. You are on a planet. The planet is orbiting a star. The star, along with a few 100 billion other stars, is inside a galaxy. And that galaxy, the Milky Way, sits in a local group of galaxies which sits in a larger structure called the Virgo supercluster, which is itself part of a much grander filament of the cosmic web. You are inside one of those lit-up nodes, one of the visible parts. The galaxies, with their stars and their planets, and their people lying in the dark, wondering about the universe. But the atoms in your body, those are a different story. The carbon in your cells, the oxygen in your lungs, the calcium in your bones, those atoms were forged in stars. In stars that lived and burned and died long before this solar system existed. When those stars ended, they scattered their elements into space. And for a time, perhaps a long time, perhaps billions of years, those atoms drifted. They became part of the diffuse intergalactic medium. They were part of the inventory that was, for so long, missing from the map. Part of the quiet, invisible mass of the cosmic web strung along a filament somewhere. 1,000,000 degrees and impossibly thin, counted in the dispersion measure of some burst that passed through and carried the tally onward. And then, eventually, gravity gathered them. Into a new cloud, into a new star, into a disk of gas and dust that became planets, one of which became this one, and on this one, eventually, they became you. You are made of formerly missing baryons. Your atoms were in the intergalactic medium. They were in the warm-hot gas that the McCourt relation weighed. They were in the filaments of the cosmic web, patient and diffuse, and part of the inventory of the universe, before they were part of you. The missing baryon problem was, in the end, a problem of location, not of existence. The atoms were there. They had always been there, we just couldn't see them. And what finally revealed them, what drew the map at last, was not a bigger telescope pointed at the gas itself, but a signal that passed through the gas and emerged smeared, and from that smear we read the count. A flash shorter than a heartbeat, crossing 8 billion years, carrying the fingerprint of every electron it met on the way. And at the end of that journey, a radio telescope in Western Australian outback, or a grid of dishes in the Owens Valley of California, or a cylindrical array in the mountains of British Columbia, catching the flash, measuring the smear, subtracting the known contributions from the Milky Way's disk and halo, isolating the intergalactic piece and saying, yes, the baryons are there, roughly 3/4 of them in the diffuse gas between the galaxies, about 15% in the halos surrounding them, 9% in the galaxies themselves. The census is, at long last, reconciled not to the last atom, not in every filament, individually charted, but in the aggregate, in the grand accounting that Big Bang Nucleosynthesis and the cosmic microwave background set up, and that the dispersion measures of localized fast radio bursts now confirm. The book's balance. Half of all ordinary matter went missing. A millisecond flash found it. And what it found was not absence. It found fullness. The space between galaxies is not empty in the way we imagined. It is full of atoms, at a density our instruments couldn't easily reach, at a temperature that put them outside most of our telescope's sensitivity, arranged in structures so large and so tenuous that they barely registered as anything at all. The void is an inventory. The gap is the content. The darkness between the lights holds most of the ordinary matter in the universe. There's something I find very settling about that. I'm not entirely sure I can explain why. Maybe it's because the intuition that the empty spaces are really empty, that the things that matter are the bright things, the visible things, the structures we can point at and name, turns out to be so beautifully wrong. The universe has been doing something in the dark all along. Not dark matter, that's a different, still open mystery, and a remarkable one in its own right, but ordinary matter. Atoms, the same stuff as everything you can touch and see and think about. It was out there, in the spaces we thought were empty. Patient, diffuse, part of the cosmic web's long, quiet architecture. Stretching between the galaxies like threads between candles, and it took a flash, a burst of radio energy from a magnetar, an ultra-magnetized neutron star, the remnant of a star that died in extraordinary violence in a galaxy billions of light-years away, to pass through those threads and tell us they were there. There is something almost absurd about it, in the best possible way. The most energetic short-duration events known in the observable universe, fast radio bursts that release in milliseconds what the sun radiates in days, and their most important contribution, in this context, is not the violence of their origin, but the subtlety of what they reveal. Not what they are, but what they cross. Not the source, but the path. In the history of astronomy, the objects that seemed strangest and most inexplicable have a way of becoming, eventually, the most useful. Pulsars were once called LIM, little green men, when their precise repetitive signals couldn't be explained. They became atomic clocks in space, probes of dense matter, tests of general relativity. Quasars were once so puzzling their name was essentially a shrug, quasi-stellar objects, things that looked like stars but weren't. They became the most luminous lighthouses in the cosmos, backlit windows through which we read the structure of the intergalactic medium. Fast radio bursts were once hypothesized, briefly, to be something artificial, an alien technosignature, a signal from an intelligence. They are not. Every studied burst is consistent with natural astrophysics. But that brief moment of wondering made them famous, and the fame brought them attention, and the attention brought the instruments, and the instruments brought the localization, and the localization brought the census. The universe does not care what brought us to the telescope, it just rewards the looking. And there is more looking ahead. The Square Kilometre Array, SCAR, is being built now. In phases, dishes in South Africa, antennas in Western Australia. When it reaches full operation, its sensitivity and its field of view will change what's possible in Ferb astronomy by a large margin. Where CHIME finds hundreds of bursts and a SCAP localizes dozens, the SCAR will find thousands and localize many of them in real time, with the positional precision to identify the host galaxy before the alert is even processed. Each one will be another dipstick, another measurement of the intergalactic medium, another point on the Macourt relation, another view into the halo of some foreground galaxy it happened to thread, another constraint on the magnetic fields threading the cosmic filaments. The partition that Connor and collaborators published in 2025, 3/4 in the diffuse intergalactic medium, 15% in halos, 9% in galaxies, will be refined. The uncertainties will shrink. The model for how gas distributes itself around and between galaxies will become sharper, more constrained, more testable. And some of those constraints will change our understanding not just of where the atoms are, but of how they got there, and what they're doing, and what they tell us about the way galaxies live and die and breathe. The census was a beginning. The partition was a step. What comes next is a map, not perfectly detailed, but increasingly precise, of where the ordinary universe actually resides. That's where we are, at the beginning of the answer. The question was asked for decades. How many baryons exist? Where are they? Why can't we find them? The answers arrived not from a bigger mirror or a deeper X-ray stare at the sky, but from a millisecond flash from a magnetar in a distant dwarf galaxy smeared by electrons it had collected across billions of years, decoded by astronomers in Western Australia with the patience and the tools to separate that smear into its components and say, the intergalactic medium, the WHIM, the filaments. They're there. And they were there the whole time. If you've been lying here, listening, wherever in the world you are, whatever time it is in your corner of the night, I hope this has been a gentle thing to drift through. A big idea, taken slowly. We started with a flash, a millisecond radio burst, shorter than a heartbeat, from a galaxy so far away that the word far barely holds the distance. And we followed that flash backward, through what it crossed, through the dispersion measure, through the Warm-Hot Intergalactic Medium, through the cosmic web, until we arrived at the number. The census. Half of the ordinary matter in the universe found at last, strung along invisible filaments in the space between galaxies. And somewhere along the way, I hope the thought settled in, the atoms in your body were part of that inventory once. They were in the gas, they were in the filaments, they were the very baryons the census was counting, before the universe gathered them into stars and planets, and eventually into you. You are not separate from the large-scale structure of the cosmos. You are made of it. Literally, the missing baryons were found, and some of them are now here, breathing, drifting towards sleep. There's a kind of deep peace in that, I think. Not everything needs to be mysterious to be wonderful. Some things are wonderful precisely because they were figured out, because someone thought carefully enough and built precisely enough and waited patiently enough that the universe gave up the answer. The missing baryon problem is largely solved. Not completely, science rarely ends that cleanly, but solved well enough that we can say we know where the atoms are. They are in the dark between galaxies, they are in the filaments of the cosmic web, they are in the halos of galaxies, calm and vast and barely magnetized. They are in your bones. And a millisecond flash, crossing 8 billion years, drew the map. If you'd like to keep spending quiet nights like this one, drifting through big ideas, one mystery at a time, a gentle like or subscribe means more than you might think to a small channel like this one. Small creators genuinely rely on your support to keep going. And wherever you are in the world tonight, I'd love to know, drop it in the comments if you're still awake. What time is it in your corner of the night? Sleep well. Dream of filaments. Close the books. Dim the lamp. Class is over, sleepy scholar.